Hello, my name is Andrew Takis, and I'm going to be proving problem number 5 on group project number 3 for calculus 3. So, what this problem is asking is you have e to the power of I times x, and you're adding this to e to the power of negative I times x, and you're dividing this by 2, and you need to prove that this is equal to cosine, except the problem explicitly asks not to use Euler's identity. So we're going to try to not use this as Euler's identity, and we need to prove this. And we need to prove this using e to the power of x as a power series. So, this is what we're going to do. The first thing that I did was I stated what we knew for sure. So the first thing what we knew for sure was e to the power of x, the Maclaurin series, is going to be equal to the summation of n is equal to 0 over going to infinity of x to the power of n over n factorial. So this is going to be equal to 1 plus x squared over 2 factorial plus x to the power of 3 over 3 factorial, x to the power of 4 over 4 factorial, and you keep on adding these for infinity. You keep on adding this forever. So we know this for sure. I would explain this in this video, except that could be a video in itself. We know this is true, and we can just use this as the power series that we're going to be knowing. We also know this for cosine and sine, but we're not going to be talking about that just yet. So, the first thing I did was I wrote out this Maclaurin series for e to the power of x. So for this, we said e to the power of x is going to be equal to 1 plus x squared over 2 factorial, and what I said earlier, but we're going to go to the power of 6 for x. We're going to go to the 6th. I just thought that was a good number. You could go on forever, except I don't have the whiteboard space, so we're not going to do that here. So, when we have e to the power of ix, what you can do is you can just put the I in all the terms with x. So, at the start we have x right here. We can just put an I next to it. For every time we have x squared, we can just say that's I times x to the power of 2. And then you're going to be doing this for every term. So this ultimately gets us e to the power of ix is going to be equal to 1 plus I times x plus I times x. All of that is going to be to the power of 2 over 2 factorial, and then we're going to add this to I times x all to the power of 3 over 3 factorial. You're going to be adding this to the I times power x, and that's all going to be the power of 4 over 4 factorial, and this is going to go on for infinity. So what's interesting is we know the different powers of I. So we know I to the power of 1 is just going to be I. We know I to the power of 2 is going to be negative 1. I to the power of 3 is going to be negative I, and I to the power of 4 is going to be just 1. So knowing this, we can determine what the I values are. We can't determine anything out just yet. So what we do is we say, well look, I to the power of 1, like I said earlier, is just going to be equal to I. And for all of these, we're just going to substitute what the value of I to that n power is for the different values. So, e to the power of ix is now going to be equal to I times x, but here we have minus 1 times x squared over 2 factorial. And then we're going to have minus I times x to the power of 4 over 4 factorial. And we're just going to go on and on for the terms that I stated here. And then from here, what we can do is we can just alter where we put that I, and we're just going to say it's, now we know there's certain terms that are going to be added and certain terms that are going to be subtracted. So from here, what I did was I wrote all of the even terms in purple and all the odd terms in green, and I put I as red just so you can see where I is in this equation. So if you can notice, all of the odd terms, so when you have x to the power of 3 over 3 factorial, x to the power of 5 over 5 factorial, those are all going to be the terms with I. All the other even terms, they all canceled out their I. Because I to the power of 2, like I said earlier, is just going to be negative 1. I to the power of 4 is just going to be 1. So, from here, what we do is I grouped these odd and even terms, and I took out that I from all of the odd terms. So, all of our even terms is going to be 1 minus x squared over 2 factorial. That's going to be plus x to the power of 4 over 4 factorial. That's going to be minus x to the power of 6 over 6 factorial. That goes on forever. All of our even terms go on forever. And then we're going to be adding this to what that I factored out of x minus x to the power of 3 over 3 factorial plus x to the power of 5 over 5 factorial. And this just goes on forever. So if you're familiar with the Euler's identity, this is getting awfully close to it, but we're not going to say it's equal just yet because the question told us not to use Euler's identity. We need to write all of this as a sum of two power series. So this is all going to be equal to e to the power of ix, right? So now we need to know what's e to the power of negative ix. So e to the power of negative ix is what we're going to be doing over on this bottom half of the whiteboard. I did it the exact same way, but I just evaluated for that negative sign. So we're going to have 1 plus negative I times x, and then we're going to have, we're going to be adding that to negative I times x all squared over 2 factorial, and then we're going to be adding that to negative I times x all to the power of 3 over 3 factorial, and then we're going to be doing this for 4 factorial, 5 factorial, we're just going to continue this. And then this is just going to go on forever. So we have e to the power of ix, but here what I did was I took out that negative 1. The negative 1, we know it's going to be I times negative 1 is going to be equal to negative I. So I didn't like that negative 1 there. I took it out just for simplifying just further. And what we can do here is we can now say e to the power of negative I times x is going to be equal to 1 plus I times negative 1 times x. And then we're going to say this is going to be added to I times negative 1 times x, all of that to the power of 2 over 2 factorial, and the same is going to go 3 to the power of 3 over 3 factorial to the power of 4 over 4 factorial. This goes on forever. So from here, what I did, very similar to what we did earlier, I just evaluated for the different terms of I. So we know I by itself is just going to be I, or I to the power of 1 is just I. And then we know I to the power of 2 is going to be negative 1, I to the power of 3 is going to be negative I to the power of 4 is just going to be 1. So I evaluated all of these i's to get rid of them, but they not all of them go away, like earlier. What we realize is all of the i's stick for all of the odd terms. So we have what we had earlier with plus I, and then we have minus 1, minus I, plus 1. So this is going to be very familiar with the last problem. And then from here, what I said is, look, we have negative x squared, because I multiplied that, we still have that negative 1 times x. So that's going to be negative x squared is just going to be x squared. You can just get rid of the negative sign. It's the same thing as saying negative 1 squared is just going to be 1. But what we know for odd terms is negative 1 cubed is going to still equal negative 1. Or negative 1 to the power of 5 is still going to equal to negative 1. So for all the odd terms, we're now going to have this negative sign. So I simplify this further to e to the power of negative I times x is going to be equal to 1 minus I times x minus 1x squared over 2 factorial. And then we have minus I times minus x to the power of 3 over 3 factorial, because that minus sign still exists. And I did this for all of them, and all of the odd terms are going to have this negative sign. So what we can further do is we can know, well, look, we have negative I times negative x cubed over 3 factorial. Those can just cancel out. So we have e to the power of negative ix is going to be equal to 1 minus ix minus x squared over 2 plus ix cubed over 3 factorial plus x to the power of 4 over 4 factorial minus I times x to the power of 5 over 5 factorial and minus x to the power of 6 over 6 factorial, and this goes on forever, this pattern. And what I did, like similar to the last one, is all of the odd I made green, all of the even I made purple. So e to the power of negative ix, and I grouped these terms together. So grouping all of the terms together, for the purple, we have 1 minus x squared over 2 factorial plus x to the power of 4 over 4 factorial, and minus x to the power of 6 over 6 factorial. The evens are going to be the same exact as earlier, except for the odds, what we have is, well, I factor out the I again, but here I have negative x plus x to the power of 3 over 3 factorial minus x to the power of 5 over 5 factorial. So all of the signs are going to be the opposite from earlier. So to account for this, in the top right here, I said e to the power of negative ix is going to be equal to, and I just took that negative sign out. So now we have what we had earlier, the x minus x to the power of 3 over 3 factorial plus x to the power of 5 over 5 factorial, and this goes on forever. And now what I can say is e to the power of negative ix plus e to the power of negative ix is going to be equal to, right here, these are all of what we found earlier, all the groups just added together. And we can realize, well look, we have the plus I, and then the group of greens, and then minus I of all the group of greens. So you could make the connection and you could make all the purples cosine, all this green sign, but like I said earlier, it didn't ask us to use Euler's identity. We're just solving using the sum of two power series. So we know that the negative i's and the positive i's, all those groups are going to cancel out. So what we have at the numerator of what we're trying to prove is e to the power of I times x is going to be added to e to the power of negative ix. That's all going to be equal to, and then this is where I know the Maclaurin series from earlier. We have cosine x is going to be equal to 1 minus x to the power of 2 over 2 factorial plus x to the power of 4 over 4 factorial plus minus x to the power of 6 over 6 factorial. This goes on for infinity. So this is what we realize all the purples are. So we can say cosine x plus cosine x is in the numerator. This is the same thing as saying 2 cosine x. So we can ultimately solve this by knowing this is 2 cosine x in the numerator, this is going to be divided by 2, and we can just say, well, cosine x is equal to cosine x. And then we can ultimately prove e to the power of I times x plus e to the power of negative I times x over 2 is equal to cosine x, knowing that this is going to be the sum of the two power series, and then we know that these are going to be equal to cosine for all of the even terms. So that's it. That's how you solve it. Thank you.